एक मिनट, दूसरा लिंक भेजा है। नहीं नहीं, वो ठीक है, एक दूसरा लिंक भेजा है यूट्यूब पे, वो वाला देख। हाँ। हेलो। ठीक है। हेलो। Hey Herschel, am I audible?
Hello, sir.
Welcome back.
Hello.
Am I audible?
Thank you. Yeah.
Okay, you can see the board also, right? Okay, you can.
Yeah.
Hanji, so where are we?
Uh,
कहाँ तक पहुँचे
we
अब?
we did the last the questions of the charges and
Yes.
Gauss's laws. Few questions. We were
Okay.
doing the basics of Gauss's law.
Okay. So I think we have to
Yes.
do the mainly we have to do is the Gauss's law, right?
Right.
Okay. So let me bring up those questions. So just a quick word on the Gauss first, before we jump in there. Let me just
Okay.
give you a small perspective on so that you first get familiar with the okay. Okay, so you might have seen this.
Which one?
The one I'm writing on the whiteboard.
Wait.
You see me?
Wait, let me find you. Wait a second. Okay. Yeah.
Right? So
Yeah,
look at
Q by
okay.
epsilon naught.
Yeah,
Yeah, I
absolutely.
have.
So look at this. Okay, so Gauss's law in fact only deals with flux enclosed in a Gaussian surface. So let me give you an example. If this, for example, is
Right.
a Gaussian surface, okay, and I put a charge in it, okay, so this Q is called as Q enclosed.
Okay.
It should be enclosed by a surface.
Right.
And if we have to calculate how much flux
Right.
is passing through the Gaussian surface, then that is given by this expression. But if I place a charge here, which is outside the Gaussian
Yeah.
surface, and this is the Gaussian surface, okay, then the flux is zero because Q enclosed is equal to zero. It is not inside the Gaussian surface. So, what is flux? Do you know what is flux? Flux is
The
E
like the
dot
magnetic field
ds,
in
where
that.
E is your
Yeah, E dot
electric
ds.
field, ds is the area through which flux passes, and the vector sign is perpendicular to the area. How? So if you have this area and the flux is passing through it, okay?
Yeah.
Electric flux, okay? Like a stream of water. Then what you
Right.
do is area, this area is this area,
Okay.
ds, okay? And what you do is you
Yeah.
draw a line which is perpendicular to the area. it's a normal to the area.
Okay.
The direction of area ds is this. The direction of ds,
Right.
the area is the perpendicular drawn on the area. So therefore you see area strangely to be a vector. Normally area is what? Meter square, right? Centimeter square. It is never a vector.
Yeah.
But in Gauss's law, when we do EDS, this represents a dot product. E dot ds is a dot
Right.
product of electric field and area through which the flux is passing. The flux is
Right.
passing through this area which I'm highlighting. Okay, so
Okay.
if you start seeing, you have numerous things to look at. It's a very busy slide. E, electric field due to a charge. When the electric field
Right.
passes through a specific area and you take a dot product of that electric field and that area, what you get as a result is a flux. So electric field due to a charge
Flux. Yeah.
passing through an area. The dot product, which is a scalar product, will give you the flux through the area. Now, what is the formula of E dot ds? It is magnitude of E into magnitude of ds into cos of angle between the two vectors. In this case, for example, electric field is in this direction. The electric field and the normal to the area, which is perpendicular to the area, are parallel to each other. Okay, so I will say the theta, which is the angle between them, is 0 degrees. So my EDS is this cos of 0 I'll put. Now what I do is I turn this a bit, and now the situation is this is my area, and now my electric field source is sending the electric field in this direction, cutting across the area. If I draw perpendicular to the area, that remains where it has to be. It is perpendicular to the area, normal to the area, and this is electric field. Right. If I have to find the flux now, what do I do? If I have to find the flux now, the flux is given by the dot product of E and area is equal to magnitude of E multiplied by magnitude of area multiplied by cos of angle between the area vector and electric field vector. Electric field vector is in this direction. The area vector is in this direction. How do you find the direction of area vector? By drawing a normal to the area. What is the angle between them now? This.
Right.
So if, for example, electric field was given to be 2 newtons per coulomb, so this will be 2 newton per coulomb into area. For example, this was 2 meters square. The angle between them, cos of 45 degrees. Assume it was 45. So 2 into 2 into 1 by root 2 is equal to 4 divided by root 2. Electric field is Newton per coulomb, area is meter square. So Newton per coulomb into meter square. This gives me a quantity called as electric flux. Electric flux is like water through the pipe. It's flux. Because you have a pipe and you have streams of water which are going through them, right?
Yeah.
It's called flux, the total lines which are passing through them. The influence of the charge is called electric field. How much force it exerts on others when 1 coulomb of charge enters their field, that is called the electric field of a charge, yes. But how much electric field is measured in another manner, which is when it cuts across a surface. So this was your surface, but strangely now surfaces have a normal drawn to them to find the direction of their area. Normally area has no direction. This is a rectangular
Right.
with length into breadth. There is no direction of an area. You just say length is equal to 1 meter, breadth is equal to 2 meters, the area is equal to 1 into 2 is equal to 2 meter square. But now it has an area, sorry, direction. How do you find the direction of the area?
Okay.
Draw perpendicular to it.
Okay.
And then obviously they will give you in the question what is the direction of the electric field. Find the angle between the two, which is this angle. So first thing you should be good
Yeah.
at is
Okay.
saying that before you do the Gauss's law, how do you find the flux through the surface? A
Okay.
Gaussian surface, right? So let me give you an example. Now this is the surface. This is the normal drawn to the surface. The electric field is in this direction, and I will change the angle. The electric field is in this direction. All right. Now my question is, electric field magnitude I is given is to be 2 Newton per coulomb. The area of this rectangular
Right.
surface is given to be, say, 2 meter square, and you can see the direction of the electric field. Question is, how much flux is passing through this surface? Flux. How would you solve this?
Uh, by EDS only,
Correct? Try
and
it. Write
then
it down. Write it down.
okay.
Let's put it to paper. Okay.
Right. So.
Correct. Correct. Right.
Right. The area is given, right?
And electric field is also given.
Right.
And the diagram is also given.
Right. Right. Um,
Right.
um, and
Take your time. I'll just give you 3 minutes to solve this. Think about it. Are you using the diagram or just blindly copying the values which are given to you? DS is nothing but the area.
yeah. Okay, I can directly write 2, right?
Yes.
Okay.
But look into the diagram. Are you using the
Okay. Okay.
diagram or not? Just give me 1 second. I'll be back.
Okay. Okay.
Yes, I'm back. Where is that you
Yeah.
feel
So
struck?
I think the theta's value, like this time it's inside
Yes,
the field, right?
you can
Just the
see.
theta's value.
You can see what I did when I was solving my question. This one, I took theta to
Yeah,
be
0.
because they were in the normal, which shows the
Okay.
area vector perpendicular to the
Uh,
area, and the electric field were in the same direction. Any two vectors which are parallel to each other
right.
the angle between them is 0
0.
degrees.
Okay. Okay.
In
Okay.
this
Okay.
case, what is the situation? That's the only difference.
These are also parallel, right?
No,
So,
I
okay.
don't think so.
Oh, it's okay. Wait. Um.
Parallel vectors have direction of the vectors in the same direction.
mm, okay. These are I think.
Right? So if you don't understand vectors properly, it's difficult. Otherwise, it's straightforward. I'm just telling you where is that you get struck, right? And that's a thought process I need to
Right.
correct, right? Unless I know where you get struck in your thinking.
I think, yeah, I'm just getting stuck in the angle part because I'm
Angle,
not
which means
getting,
you
okay, yeah,
the
theta.
understanding of vector. Two vectors
Okay.
and
Yeah,
and what is it? How to find the angle between them? That is where you're getting struck.
right.
Chal, I'll give you 10 more seconds to think about it.
Okay. Um,
All right, let me help you out. Just give me one
right.
second. Okay. These are anti-parallel vectors, so the angle is 180
Right.
degrees. If there are two vectors which are not in the same direction but
Oh,
opposite direction, the angle
yeah.
is 180.
Okay. Okay. Could you repeat how we got 45 in
Yes,
the
yes,
angle here? No?
yes, I can. Now you are curious, right? Earlier did not understand. The the area is visible to you, right? The area,
E- this part. Yeah. Yeah.
the
Yeah. Yeah.
rectangle is visible.
Yeah.
I have drawn a perpendicular to the rectangle, which is this.
Okay.
But the electric field is passing through it at something like this.
Right.
Now, if you notice, the electric field is like this, and the normal to the area is this, right?
Right.
What is the angle between the electric field vector and the normal to the
In normal
area?
vector.
It is given to be,
Oh, okay.
and that is why I used
Okay. Okay. Okay.
45
45.
degrees. Clear?
Right. Okay. Yeah. 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 I got it.
Okay.
So it's like a standard value.
Standard of
The angle between electric field and N is,
is what?
yeah, like the value of is 45 degree.
No, we use 0 degree here.
That's like
We used 180 degree here. In the question, it can be anything. Who says it is fixed? This particular situation, it was 45 degree. In some other situation, it can be 60 degree.
okay.
So when you are working on the
They told
flux,
us it's 45.
yeah, I mentioned it.
Okay. I didn't hear that part.
Okay. So if you
Yeah,
have to
that's why now it
calculate
makes sense.
flux,
Yeah,
you have dependency on how much area is involved,
yeah,
area of the surface through which the flux is passing. You have dependency on the electric field, and third, you have dependency on what is the angle theta between E and area vector.
right,
These are the three things you're dependent on. So you're
right.
dependent on the magnitude of E, you're dependent on the magnitude of area, and then the cos of angle between them. So E can be anything, area can be
Okay,
anything, and so theta can also be anything. There is no fixed rule.
right.
Got it?
Yeah,
So electric flux is an important property of the electric field. Electric field is vector. E is a vector, right?
yeah.
But flux is a scalar.
Okay.
Got it? All right. Any doubts in your mind pertaining to this?
No. I got it now.
All right. Tell me what, as per. So, if you notice the Gauss theorem, let me take you back to the Gauss theorem. Gauss theorem has all of this involvement. It talks about flux, it talks about E, it talks about ds. Though we have focused on the learning of flux, but we are actually studying Gauss law only. But we have studied one part of the Gauss law, which is the EDS, but we have put an integration sign. Do you see that? The integration is
Right.
equal to flux, because integration means this is a very small area. If you add all those areas, then you get the bigger area, which we are anyway using in a formula. Like we're given a
Okay.
rectangle, it's a bigger area, right? We are not using ds. ds is a small
Right.
area. So,
Right.
so what you were studying as a flux, actually, you were studying the Gaussian theorem, but you still don't know. Though you have some sense of flux, you still don't know what is the Gaussian theorem. Tell me what, as per you, is the Gauss law. Whatever you learnt.
Gauss's law is it was the definition, like it's 1 by epsilon or pi times the electric charge present in a,
Correct. Correct. Okay.
that's what, yeah.
Okay. No problem. So see, Gauss law, what it deals with, if I were to tell you this, is that it gives you a relationship. So let's rewrite it. Okay. E dot ds is equal to flux is equal to q up. One more entity has got introduced. You studied this part of it a bit,
Yeah.
but you don't know what is this. Gauss law
Epsilon
gives you the
naught.
power, to find the relationship between quantities which were not related to each other earlier. For example, if you were to find if I tell you that I have this cuboid, okay, I have a cube like this, okay, I have a cube. I will just draw it.
Right.
This is my cube, okay. Now if there is a charge inside this cube, it's a positive charge. If there is a positive charge, you know the electric lines of forces will go away from it.
Right.
So these lines are going in all direction across. They're coming outward, leftward, everywhere they are the same. This is the way they are moving. Now, somebody tells me I have, using some method, been able to tell the flux which is passing through all the 6 surfaces. Some gentleman says, I am able to find the flux passing through all the surfaces. I know it. So I
Right.
said, okay, what do we do with that? He said, since I know the flux, I can tell you how much charge was inside that surface. He found out the flux and he said, flux is equal to
Right.
Q upon epsilon naught. Now the value of epsilon naught is known to us. It's the permittivity of,
So your voice went away.
okay, is it better now?
Oh yeah, I can hear you now.
Yeah. No, I said some gentleman was able to find the flux associated with the charge directly. He had some method to find the flux through the surface.
Right.
Right? Then he said, do you know, by the knowledge of flux, I can tell you how much charge was enclosed in the surface.
Right.
Said, okay, let's do it then. He said, use this formula. So in the previous section, you learnt what is the flux.
Right.
And you learned that flux is right? This is not the magnitude, right?
Yeah.
It's just a cos theta. So just
Yeah. Or not cost. Yeah.
yes, right. You learned that in the previous section. In this section, what you're learning is this: that how do you relate the flux with the charge? See, flux finally, where does the flux come from? Where does the flux come from? We were drawing these diagrams. We have a area.
Yeah.
There is a flux passing through it and stuff like that, right?
Yeah.
This is a cube. Inside a cube, there is a charge. And due to the charge, there is a flux.
Right.
Somebody said, now you know the flux. Gauss, what he did was he linked flux and charge. In this formula, do you see any mention of charge? No.
Not really.
You see
Yeah.
electric field,
The electric
you see
field,
the
there's the
area,
angle, and
you know the angle between the electric field and the area. There is no mention of charge at
yeah.
all. But Gauss was very intelligent. He
Right.
said the same flux is linked to the charge like this.
Okay.
Which charge? The charged enclosed by the surface. So do you see that a cube is enclosing the charge? The diagram, what does it show? a cube is enclosing the charge, right?
Right.
And someone found a way and calculated the flux through all the surfaces, 6 surfaces of the cube. So somebody found out this value of this flux, which is shown like this, which I'm drawing arrow on. Someone said, I know the value of this flux. I have a way to find out. He found out this. Gauss told him, then I can tell you how much charge is enclosed in this surface with this formula. So Gauss told him the charge inside this surface is equal to phi into epsilon naught coulombs. So if
Okay.
you know flux in an enclosed surface, then you can find out the charge in that enclosed surface.
Right.
This was the contribution of Gauss. He could link the charge and the flux. Let me give you an example, okay? Let's say you have a situation like this. This is my Gaussian surface which I've drawn, okay? There are two charges in it, 4 coulomb and -2 coulomb. Okay? The question is,
Yeah.
if you know the charges enclosed in the Gaussian surface, please tell us the flux associated
Yeah.
with this Gaussian surface. How much flux will be cutting through this surface?
Right.
How will you do this? The concept is this. But now I've given you two charges.
Q enclosed. Okay.
Yes, sir. Are these two enclosed in the surface? Yes or no?
Right. They
They
are.
are. They are. So what is Q enclosed
So you
going
can
to be?
add them.
Yes, I can.
Uh,
Allowed.
two,
Tell me.
2 coulombs. 2 coulombs.
2 coulombs. Agreed.
Yeah.
So 2 coulombs is equal to flux, which you have to find out. The medium is this. So how much is the flux enclosed by the Gaussian surface?
Uh, 2 q by epsilon
This
naught.
is a fixed
That will
quantity, right?
be around. Yeah.
So if you have to establish a relationship between charge enclosed in a Gaussian surface with
Right.
the flux enclosed by the Gaussian surface, this is the way to go.
Okay. And then epsilon naught's value is the electric field.
Permittivity.
Oh no, or like we can just right,
Huh.
we can
Yeah, yeah.
directly
It is
substitute
given. You can. Yes, you
8.85
can.
million.
You can.
Okay.
You can.
Yeah, yeah. Okay. Okay.
So the word is, remember this word,
Okay.
enclosed.
Right.
This is the way to go. Right? Very simple and a straightforward kind of situation which you have to memorize. So the flux through the
Yeah,
closed
I got it.
surface. Okay, this is a closed surface. Now let me give you one more question. So we have a Gaussian
Right.
surface. The charge here is 2 microcoulomb, and then there is a -6 microcoulomb. Question is, what is the flux enclosed by the Gaussian surface?
There's okay. Um, U by epsilon naught. Mm, mm. 2 by epsilon naught?
Hmm?
Is it 2 by epsilon naught?
Yes. Don't include 6
Yeah,
because it is not
2 by epsilon naught.
enclosed. You will always worry about enclosed. You will not worry about the one which is not enclosed.
Okay.
Okay. Now, let me just connect all the dots. We started with knowledge of E dot ds is
Cos
equal to
epsilon.
phi.
Yeah,
Then we put in an integration sign because we are not dealing with ds but by larger area. The integration means adding of all the small areas. Then calculating flux through each one of them and the total flux sum comes out to be phi enclosed.
right.
Then we said phi enclosed can also be written as q upon epsilon naught. We can link the flux you have calculated with the charge enclosed by the surface. This whole expression which you see with an
Right. Q by
electric
epsilon.
field, there is an electric field, there is an area,
Yeah, vector.
correct?
Yeah.
The flux enclosed, the Q enclosed,
And the, yeah,
the permittivity of the medium, all of them together
right.
have to be dealt with. And who brought this whole thing together?
Gauss. Yeah,
Okay. Now, very interesting
yeah.
fact. Very interesting fact. See, Coulomb said electric field due to a point charge can be k q by r square at a distance of r. So electric field due to a point charge q. Point
Right.
charge q. R, what is r? Distance at which
Distance from the charge.
electric field is
Okay,
being
this.
found out
Okay,
from the charge. Yes.
right.
If I tell you this is only for a point charge, right? For example, this charge. This is a point charge, right? And then I can tell you there is another point charge,
Right.
another point charge. There are square. What is the resultant here? You will start applying vector knowledge and solve the answer. Q1. We did many numericals like this. Find the resultant here. So you said this is repelling, this is attracting, this is repelling, repelling. Let's do resolution of vectors cos theta, sine theta, and solve it, right? So you can find electric due to a point charge very easily with the help of Coulomb. Coulomb-like expression, right? But now I will give you a situation. The situation you have a line charge,
Right.
which is not a point charge. It is an infinitely long charge. It never ends. This is not a point charge. Such charge distributions on a line which are infinite are called as continuous line charge
Could you
distributions.
repeat? Your voice was cracking for me.
Okay, no problem. So this is a situation of point charge.
Yeah.
But this is the situation of continuous line charge. A straight line having charge
Continue. Okay.
continuous, and the linear density it has is lambda. That means how much charge per unit length.
Okay. Right.
Now my question is this. Look, can you see the difference? This was only a single charge, single charge, single charge, single charge, single charge. And you could use these expressions. But now you're going to be in deep trouble because you don't have a single charge. You have an infinite line charge situation, which starts from minus infinity and ends at plus infinity. If I tell you find the electric field due to this, find electric field due to continuous
Continuous line charge.
line charge distribution, you're in dilemma. It's very difficult.
Right.
You can use Coulomb's law, which is this type of law, to find the answer, but it'll be a lot of mathematics involved. A lot. So what Gauss did was, so this is what I'm writing. We can calculate the electric field due to an infinitely long charge, okay, using Coulomb's approach. We can, but it is very difficult as it involves a lot of knowledge of integral calculus. There is a way you can use approach to find electric field due to a positively or a negatively charged electric. For example, you have to find the electric field here. Question is find the electric field due to this whole infinitely long charge density, linear, this lambda here. Find the electric field here. You can, but Gauss gave a very simple solution. Gauss gave a very simple solution. No need of any mathematics. No need. He said, I can help you solve this problem without the knowledge of too much maths. There is no need. And otherwise you can, but it becomes a very long drawn effort. This is what he did. He said, okay, this is your, so let's see what is that Gauss did, right? So he drew this infinitely long linear charge density like this. And then what he did was he said, okay, so you're where do you end? I said I'm going to never end. I'm at running to infinity, and on the bottom side I am running to minus infinity. I am endless. Find the electric field very close to it at a perpendicular distance of r. Right? This is what the problem that was given to Gauss, and he solved it in a very, very elegant method. What it did was he took a Gaussian surface to enclose some charge of this infinite density. He took some. He said, "Okay, I will take a part of this." And what he did was he drew a cylinder. He drew a cylinder, and he said, "Let the length of the cylinder be some value, okay, L." And he said all these charges have an electric field, and electric field also has a flux associated with it. Then what he did was he said, I'm going to apply the Gaussian law to this cylindrical Gaussian surface. So he started with what? He drew a cylindrical Gaussian surface of length L, which you see, and radius R, which is the radius at which you're supposed to find the electric field. The distance, this one. And then he said, now my question to you is, how many surfaces are there in a cylinder? If I say, first question, does this cylinder enclose any charge? The cylinder drawn by the Gauss, an imaginary cylinder.
Yeah.
Does it enclose any charge?
Line charge, right?
Yes, of length L, right?
Yeah.
If I tell you the linear density is lambda, which is a charge per unit length.
Yeah, line charge density, lambda.
Correct, per length. Then tell me, in length L, how much charge is enclosed? So 1 meter has lambda.
Okay.
L will have how much?
Q by L? Okay, no.
Q is equal to?
Yeah, lambda into L.
L. This was
Right.
per unit length. Charge per unit length multiplied by length tells you the Q enclosed, right? So now you know how much charge is this from here till here, right? Which I'm highlighting now with a different color. So now we know which one is the enclosed charge. Okay. Now
Right.
tell me, if I look into the Gaussian surface, which is a cylinder, tell me the surfaces you're referring to. How many surfaces do you see in a cylinder? The top surface?
3.
Bottom
3, right?
surface? Yes.
And the
And which one?
rectangle. The rectangle.
Yes, which is the curved surface.
Yeah, the curved surface.
All right. Now, if I were to draw a normal to the, I have to, now I know that EDS, as told to me, was integration of E dot ds is equal to Q upon epsilon naught, right? So, supposingly, if I were to draw a normal to this area, so this area I called S1, the area below I called as S2, and the curved surface area I call as S3. There are 3 areas you told me, right? So that means if I were to calculate the flux through them, I will have to draw 3 normals, right? First normal here, second normal on this, anywhere. It's a curved surface area. A third normal. Okay. And I know there is a charge also enclosed in it, which is this quantity. Okay. Now what I'm going to do is I'm going to calculate the flux passing through what is the flux passing through the Gaussian surface? Passing through the Gaussian surface. Okay, let's calculate the flux one. So the total is going to be the flux through S1 plus flux through S2 plus flux through S3. All these will tell me what is the total flux associated with the enclosed charge. How much flux is being given by the enclosed charge to the surface.
Right.
Right, exactly. So let's calculate the first one. E dot ds. Now tell me the surface number 1 and surface number 2. Where is the direction of E if it's a line charge density? The electric lines of
Right.
force will be on both the sides away from the
Yeah.
charge. And the normal is here. What is the angle between the electric field and normal now?
Uh, 90.
90. So cos
Yeah.
of 90.
Right.
That's my first surface taken care of.
Right.
Let me go to the second surface.
Oh yeah, both S1 and S2 are 0 and the pi ds1 will be E.
Third surface, the curved surface, right? Now,
Yeah, it'll be that.
the electric field is going like this everywhere. And same is true for normal, right? You can draw a normal also on a curved
Right.
surface like this. If you have a curved surface like this, you can draw, if you can draw an electric field in all the directions. And same is true for normal also, right? The normal can also be drawn like that. So the normal to the curved surface will be parallel to the electric field everywhere. If you have a glass in your hand and if you draw perpendicular to the glass, a cylindrical glass, this is your cylindrical glass in which you drink water. Draw a perpendicular on it towards you. And if there is a line charge which is going, draw perpendicular to there also towards you. They will be parallel to each other. This is a normal to the area. And the other one is a normal, which is the electric field, because electric field is coming out of the paper like this. Electric field is in all the directions, except upwards.
Right.
Right? Except upwards.
Right.
Upwards there is no electric
Yeah.
field. But as far as plane goes, if you are in this plane, it is everywhere.
Yeah. All directions.
Agreed? It is like this.
Yeah. Yeah.
And the normal to the plane, if this is the curved surface area, the normal is also in all the direction. Anywhere you draw is perpendicular to the surface, the curved surface. So for the third curved surface, the situation is going to be that the third one, with this one, curved surface area, it will be E dot ds cos of 0.
Okay.
So this is 0 because cos 90 is 0. This is 0. So what is the net
0.
answer?
ds cos 9.
How much is the curved surface area of a cylinder?
2 pi RH.
2 pi RH. L. The length is L, right? And it is
Right.
cos 0. So dot product taken care of into 1. So now we have calculated what? The flux cutting across all three surfaces. On the two
Right.
surfaces, actually, there was no flux because they were perpendicular to the electric field. Only in the curved surface area we were able to find the flux. So now we know the total flux associated with this Gaussian surface, which is the cylinder. We calculated flux, right?
Right.
In the next step, he said, okay, now that you know that flux, and you know the flux is to be written as Q
Q
upon
by
epsilon naught.
epsilon.
So he said, okay,
So
I'm going to
E
write my
into pi
flux as E, electric field due to the line charge density
Oh,
multiply by 2 pi RL.
yeah. I know this one. I remember this. We did
So
it
you
in
do.
class. We did the
Okay.
derivation.
Yes, has to be remembered, has to be memorized and understood. And therefore,
Mm.
electric field comes out to be.
One. Okay. By 2 pi r into Q. Yeah. So sigma by 2 pi
Yes.
E epsilon naught R.
So this, what is the conclusion? Obviously, you're able to find the electric field due to a charged density which is continuous. It is not a point charge like this. It is a continuous charge. And it is uniform of this much line density. The point you've also made, apart from doing a grid derivation very simplistically, so this was a, if you look at the Coulomb's way to do the same thing, it is very difficult because it requires a lot of knowledge of integration. One more conclusion is, apart from its mathematical simplicity, you also realize one more thing when you look into the way we solve this. Do you see anything else apart from the mathematical
Right.
simplicity?
Right. It's
It is
easier.
mathematically simple, pretty simple
Yes. It's easier.
enclosure and all of that stuff. Like, and you can
Right.
find the electric field density also. Great advantage. One more important lesson for you is, what is the mathematical simplicity all about? It is about finding electric fields due to continuous charge density which you cannot find otherwise. For point charges, Coulomb's is very handy. If you have point charges, use Coulomb's law. But if you have a continuous charge density where there is some uniformity, like a uniform line charge, use Gauss. So Gauss law is also extensively used to find electric fields due to uniform charge densities. That's another usage and application of Gauss law. Finding electric field due to continuous charge densities. Application
Right.
of Gauss law. If they ask you what is the application of Gauss law, one of the answer you can give is, we can use it to find the electric field of continuous charge densities. So if they say,
Right.
what do you mean by that? Of course, you have to memorize this formula. And remember, if it's a positive charge, then the electric field is like this, the way I'm drawing. And can you see the electric field is inversely proportional to the distance from the line charge, where r was the radius of the cylinder, right?
Right.
What is this, which I'm darkening now? Let me just use some different color and show you the
Which one?
distance. This one.
That's the radius R.
Yes? Isn't that the distance from the
Yeah, the
line charge
distance from the
density?
line.
So look into your expression. What have you got as the expression? Look at this.
Right.
2 pi r L and epsilon naught. If I collect these two, the charge on that L length and L, what will they be called as? It is nothing but lambda. The total charge enclosed on length L. If you divide these two, what will it will give you?
Yeah.
Because what is this
Sigma bar.
Q? The Q which we are talking about, what was? It should be the
The charge.
enclosed Q, right? So this cylinder is enclosing some charge, right? The whole this charge is Q. Obviously, it is not a point charge. It is linear charge. It is distributed on a line.
Right.
and it is a vector. It's a vector. It is not a scalar. So the electric field is away from the line if it is positive line. If I draw a negative line, what happens?
Negative.
Towards the line, the electric field value will remain the same, but the direction of the vector is going to reverse. This is the electric field now.
Right.
If it
Yeah.
when the charge is negative,
Okay.
so they can give you lambda to be plus 2 microcoulomb per meter. They can also give you lambda to be minus 2 microcoulomb per meter. Any value can be given, but you have to be very careful about the signs, whether it is plus or it is minus. Any doubts in your mind so far?
No. Got it.
Making sense, right?
Yeah.
Okay. All right. Should I move forward?
Yeah.
All right. Now let's do a numerical
Okay.
on infinitely long charge density. So you have two line charges. This is positive. It's an infinitely long charge. So I will indicate that minus infinity to plus infinity, minus infinity to plus infinity, and this is my negative charge. My question to you is find the electric field. The distance between them is given to be
Right.
0.1 meter.
R.
Wait, r is always the distance between the charge and the place where you
Okay.
need to find it. I have
Okay.
not told you the place at which you have to find. I've just told you the
Okay.
distance between the two.
Okay.
Okay. Let's say you have a point which is line which is in middle of the two charges, right? So
Point which is
what
like, yeah.
it is, okay, and what was the distance between them? I told you the distance between
1.
question is what is the resultant electric field between the two linear charged densities of infinite length given lambda A, this is A and this is B. The lambda due to A is given to be 2 microcoulomb per meter. The lambda due to B is given to be minus 3 microcoulomb per meter. You have to find the net resultant electric field due to the two charges right at the middle point of the two infinite. So which means you have to find all through here. But if you find it one, it is same everywhere on the line. Middle point. So and the distance between them is 0.1 meters. And you know the concept by now that the total, if you have to find the electric field due to an infinitely long charge, this is a formula you're supposed to use. So the concept is known to you.
Yeah, we should use 1/2 pi epsilon naught r, right?
What else have you studied?
Formula.
For an infinite length, this is
This
the
only.
only concept we have studied, right? We have not studied anything else. So
Right.
yes, my answer is yes.
Oh yeah, sigma.
And the second thing we have learned is it's a vector, and we should be careful about the directions of the vector. Which are you finding? The electric field due to A or B? So you're okay, you've written the concept. You will use this. Okay, fair enough. So you're doing the solution in board examination. Your solution is based on your knowledge of the fact. You will first write an electric field vector. Okay. Now what? Now what? Next step.
Okay.
So I give you one marker for.
So I should
You're
find for
correct.
A and B separately
Yes, please do that. Please do the
and
honors.
then add them.
Yes, vectorially.
Okay.
Add them vectorially, giving due importance to their direction. Because these are not rupees to be added, these are vectors. You will apply vector addition.
Right.
You keep epsilon naught as epsilon naught. Don't worry about it.
Okay. And R is
Middle of this. The distance between them is known. So what is R? From the positive side?
the half of
Exactly. So
0.1
0.1 by 2. 0.1 divided by 2.
Okay.
Take 2 up. You can take 2 in the numerator, right?
Right, I can do that. I'll just do that.
Fair enough. So you get 2 cancels. There is a 0.1 also down below. Pi epsilon naught, and 0.1 can become 20 here, right? If you take 0.1, 1 by 10. So 10 goes up, this becomes 20 upon EA. So you got the EA, Newton per Coulomb. What is the direction of this vector? What is the direction
Newton
of...
per Coulomb, right? Then E for B.
No, hold on. What is the direction? What is the
Direction EA is direction of the vector EA. It'll go
EA.
towards
Towards what?
Okay, this is A, right?
Yes, and it is positive, and I've told you
Right
already.
side towards the...
That is correct. So please
towards
write.
B.
Correct. So write it down. Write it down. When you found your EA, right? Right here towards right.
B. Okay, towards right side. Okay.
Okay, fair enough. Let's do the B one. So now you started with the knowledge of continuous charge distribution, and now you have ended up doing a vector exercise only. That's all. You're adding 2 vectors finally.
Right.
Right. Everything finally reduces to what? Vector.
Right. The charge is negative,
Negative. And I've told you already, you can read above.
right?
It is, and I've also shown you the direction in a negative way. Look at this. I've told you what is the direction
Toward
of electric field.
negative is going leftwards,
On its left. Now you are worried about this
but
part. On its left.
right,
So
right,
you can see the diagram and you can draw the vector. What is the direction of this vector for a negative charge on the left? It is towards the line charge.
left
Okay.
towards the line charge,
Yes. So which means what? Towards the center or away from the center? Because
towards the center.
you're finding the E here. So due to the negative charge, the electric field is in which direction? Towards the center or away
Towards
from
the
the center? Or you said
to,
A and B, right? Towards B or towards A?
sorry, what?
Towards right or towards left? You did not say that.
Towards the left, towards the line charge.
Which line charge? That is towards left.
Like, but it's on, wait, but it's negative.
Apply yourself. It's not that hard. You're
I
finding
think
it
it's
here, right?
also
You're finding
rightwards
it here.
only, but
You're finding it here.
the charge is here and we're finding it here, it should come here, right? What's in yeah, towards left.
Okay, write it.
Yeah, right, towards left.
Now you have to add the two vectors. Knowing fully well, you can also write I, J, K if you want to. Use the knowledge of vectors.
It's towards, so it's towards left only?
Towards left only. How do you say that? Can you draw the vector for me so that I know it's towards left? If I were a guy
Like,
sitting on your negative charge, if I were sitting here, I will see the electric field coming
right,
towards me. That means I will see coming like this.
right. But from the negative charge, is it still going towards the right side?
Yes, it is. But what
Okay, so
about
both are
where are you finding? That's my question. At the center. What does a
whatever.
guy at the center feel? If I am sitting here, what will I feel? What is the
Right.
direction of electric field if I'm sitting here due to the negative charge? Draw an arrow. If I'm sitting at the center, if I am
Due to
sitting
the
here,
negative charge.
what is the electric field direction I will see?
Pulling
Draw that.
towards itself.
Draw it. Don't say it. Please
This.
do. Physics is not English. Okay. Agreed.
Okay, okay.
Agreed. Yes. No. Where is your
Yeah.
arrow? Oh, I have drawn so many arrows here. How can the electric field be away from a negative charge? I have told you here above. Due to a negative charge, the electric field has no other option but to be towards the charge.
Towards the line charge or towards the negative?
Yes, towards the negative. Why have you drawn this? How is this towards the negative? This electric field is
No,
away
like
from.
if the negative charge here, okay, but it's going towards the line charge in the center, right?
No, it is not.
Like,
That is only
oh,
possible if you are positive. The electric field due
the
to a
line
negative charge has to be away on either side. Whether on its
right.
left, whether on its right. So why was your towards the charge? Is my question to you.
Because I thought that it'll go
You
towards
thought
the
there is a
line
rule to it. You know, your thinking
charge
does not
to
matter.
because the negative, yeah,
It doesn't matter. There is a rule.
right,
It has to be towards the negative charge. This is a
right.
situation of
Okay,
positive, which I've drawn just now. This is for positive.
right.
Now draw the electric field at the center due to negative charge.
Due to the negative charge at center. So like this, right?
Yes. And so, which
Okay.
means, can we say that both the electric fields actually are in the same direction?
Yeah,
Add them like numbers then. Because they are collinear, they are in the same direction. The one due to positive charge
yeah.
is like this. The due to negative charge is like this. So they are getting added. And so don't worry, don't get
Right.
scared of this
Like,
particular negative sign.
do I still have to take it into consideration,
No,
right?
no need.
The negative.
No need.
Okay, so I can just add them. No need
Yes,
of
because you
canceling the
first
charge.
find
Okay.
out the answer.
Right.
Newton per coulomb.
Yeah. Right. Right. 50, right?
Yes.
50
20
by.
plus 30. 20 plus 30 is always 50. What is there to worry about? You have a worry for
I
that
could
also.
just cross check it.
20 rupees plus 50 rupees is how much?
I don't know, but yeah.
Make sense?
Right.
Okay. Next question. I hope it gave you insight. It was a detailed
Yeah.
discussion, right? You're doing error, I'm correcting you. You're doing error, I'm correcting you.
Yeah.
That's how you learn physics. You don't learn physics
Right.
sitting in a group gossiping or listening to lectures. You have to find a guide who tells you where are you going wrong. And then you have to go back and study for 2-3
Right.
hours, which is called self-study. Otherwise, what will you cut
Right.
instead of human bodies? Onion. Okay? Next question.
Right.
If I were to tell you for an infinitely long linear charge density, please draw a graph of E versus R here. Electric field versus
Mm,
R. How will you do that?
like this.
I have already shown you where you're supposed to draw.
Nuclear.
Please draw it here.
Oh, it's going there. Okay, okay, 1 minute. Need to find. Uh, 1 minute.
This is your logic.
Yeah, I should draw it here where you are
Wherever,
right now.
yeah, wherever you want to. Here.
Okay, I found you. I found you.
Hmm.
Found it. That should be. Oh, okay. Like this.
Agreed. How did you explain me? Explain me. What did you do?
How did I what?
Yes. What is the rationale to draw this? Explain me.
Uh, The R is the
R
distance
is
between them will decrease
between
with the
them. Who?
increase
Amitabh
in
Bachchan
the
and Vinod Khanna. Between whom?
no, the distance between the two charges
No, there are no two charges here. There
from
is only one
the
charge.
line
No,
charge,
no,
like from the
no,
line.
sorry, disagreed.
So
There are no two charges here.
the infinitely long wire and the charge.
There is no charge.
No, I meant the infinitely long wire and the
And the point at which
um
electric field is being found
okay,
out
then the point okay, the point at which electric field is being
is being found out
found out and the
due to the
um
due to the infinitely
infinitely
long
long wire.
charged. Yes. The distance is not distance between any two
Right,
charges. I'm sorry. It is the distance at which you are finding the electric
right,
field.
right. Okay.
Explain me. How did you draw this? What was the logic? Although you should have drawn it properly,
Um,
I would have drawn it more like this. Your R has
yeah,
started increasing from here.
yeah, that's
Electric
true.
field has started going up, which is weird. My answer is this, which I've drawn. Okay, my answer
Right,
is that. So you can draw again. Please draw
like
it nicely.
this.
All right, redo it. I will just clean it up. Redo it and draw it properly.
It
Yes, we will. Don't worry. Still
better, I
slightly
guess.
better. But remember, R should continuously, yes,
Yeah, this is
electric
better.
field makes sense. Fair enough. I will go with that. Explain me the logic.
Uh, Basically, the electric field is inversely proportional to the distance at which the point
Distance at
from
which,
the infinitely long wire
hmm,
is considered.
agreed, where you are finding the electric
So
field.
they're inversely proportional.
Yes. So which means
Yeah,
R
that I'm
will
finding the electric
increase,
field.
the
So they're
distance will
inversely
increase, the electric field will go down. It is reducing, right?
decreasing. No,
Yes.
it's inversely proportional.
Yes.
Oh,
Correct.
it's
Inversely.
yeah, yeah, yeah.
Okay. Now you
Makes
get it,
sense.
right? Don't forget that you have to be very accurate in what you do. Okay. Let's change the question, and this is the last
Right.
part for you today. Tomorrow we will do class 11th. Okay. Today you're doing
Okay.
class 12th. If you don't get a
Right.
strict teacher
Okay.
to work with, he's probably making a fool out of you. Your dad's hard-earned money. And if I don't get a student who
Yeah.
is hardworking, that student is making a fool out of their parents and the teacher.
Right.
All right. Okay. So let's say these are the
Are you
two.
writing anywhere right now?
Yes, I'm writing on the board the way I do.
Okay. Okay. I found it.
Yes. Again, this is 2 microcoulomb per meter. This is minus 3 microcoulomb per meter. At what, and the distance between them is zero point 0.1 meter.
What is the?
What is the question? At
Could you
what
repeat
point?
the what?
Yes.
Yeah, the question. Yeah. At what point?
Wait, just answer him.
Yeah. At what point? Okay.
Well, I'll just, okay, let me ask you a simple question. I was somewhere where I am not able to wait. Mm,
Your
I will just write something. Wait. Okay. So I'm coming back. My question to you is,
yeah,
what is the electric field at a point?
right.
At what point is the electric field zero between the two continuous charge distributions? So this is plus and this is minus. You already know that.
So at what point is the the electric field zero? Is that what you said?
Yes.
You're writing it. Okay. What point between the positive terminal long wires is the electric field resultant zero? Just- Okay. Okay, the distance is zero, and they asked us what point between. Should I like give a point or like
Yes.
that? I should solve it like that.
Assume let the distance of that point or
Mhm.
the line group of
Okay.
points be x from
Uh,
this. Then the balance distance will be
what
zero point 0.1
charges
minus x. Let
point?
me complete. Let me complete first. When I, yeah.
Okay, okay.
Yes. Yeah, obviously. Got it? Okay. Where
I
is your
should solve it
point?
now.
Show me that
Okay,
point
I'll draw it.
which you're
1 minute.
considering.
Uh,
You have to
it
draw a
should.
diagram
Okay,
first.
if the both the charges diagram. Okay. Mm, the- uh, Mm,
If I were you, this is what I will do. I
resultant.
will say let this be the place at which the electric field is 0. Let the distance be x.
Okay.
So the balance will be 0.1 minus
Okay.
x. Then I will write the individual electric fields, add them up, and put it equal to, and find x. Because I'm given the condition that electric field resultant is 0. I said let the distance of that point from the 2 microcoulomb be x.
Be
So the balance
0.
distance is 0.1 minus x. So now I've drawn the diagram for
Okay.
you.
Okay. Minute. Mm, If okay. Distance between. So okay.
Do exactly what you
Can we
did in
get
the
them
above
A
question.
and B? Right. Electric field. Okay.
Vector
Take that
addition
A.
plus
B.
EB. Okay, you want to do
Right.
it on your own way, do it. Do it. Okay, okay. I'm good.
EP. Like I can do it like this, right?
You can, you can. That is the only thing you've learned today.
Okay. Okay.
So you will take
Right.
R to be X.
Okay.
X, right? The
So
distance at which
it's
you're finding.
epsilon naught. Uh,
I'll just be back.
yeah. Okay.
When I think of a dishonest politician, अंदर से आता है.
Okay. They said basically EA vector plus EB vector is 0, right?
Correct.
The distance. Okay. So
And you know the you have to think in your mind the directions because one is positive, one is negative. You just did it. In
they
between them they
both
get
in the
added like
same
numbers.
direction.
Exactly. Good.
Yeah.
So डांटने से बहुत फर्क पड़ता है. बच्चों को डांटो.
Um, um,
Just be careful. Okay, so calculation is yada yada yada. Okay, correct. So I've just put in a small highlight here. Please ensure that your microcoulomb is converted into
Yeah.
coulombs.
We can do that in the end, right? Because it's
Yes,
just given
fair
as
enough. It'll
x
anyway
right now.
vanish because it'll come as a common, right?
Okay.
It'll become 0 anyways. But okay, now solve it. So takes from numerator denominator also you can take a lot of stuff common
Yeah,
and common
that's all. So,
and put it equal to 0.
1 by x.
You're not putting it
Yeah,
equal
is
to
equal to
0.
0.
You're just writing
Yeah,
it
yeah,
like
yeah. Okay.
so. This cannot be
Right.
0. This cannot be
I got
0.
it. I got it.
So this is 0.
We can bring it the other side. I can just bring it the other side, right? This part. Divide me, then it'll become 0.
Bag.
2, 1. I got this one the other side, like I transposed it, so that
Yeah.
became 0.
So this is cross multiplication
Okay.
0.
Right. 2
Hey, this was
minus 2.
0.1 by the way, okay? 0.1.
Oh.
Just be very careful.
I thought he wrote 1. Wait. I'll
No problem.
just erase it. Okay.
And therefore the other one was 0.1 minus x. Yeah, you have already, okay, fair. So you have done that, and this is 0.2. Okay. So
0.2.
Okay. Yeah.
Plus 3x. By 2x minus 2x squared. It's okay now, right? 0.2, 0.2.
Equal to 0.
Yeah, equal to 0. Okay. 3.0 minus, which is 2.8, I think, but okay, just do it. Yeah. 0.8 to 1.
Equal to 0. You don't need to write denominator. It's gone. Just cross multiply it.
Oh yeah, I'll just, yeah.
How many
Okay.
times will you write?
So,
Not required.
is to 2. Okay, no, wait. I'll just, wait a minute. Yeah. 2 is equal to 2.8x. I'll add it this side. So x is 2 by 2.8. Right? So is 1 by 1.4. Can I leave it like this?
Show me.
Into 10 to the power minus 6.
How did you get 10 raised to power minus 6
Like
suddenly?
this. Wait, wait. I didn't. Okay, wait, no.
That had
Sorry,
become
sorry.
0.
Yeah, I'm just checking that.
This whole thing had become
Yeah,
0.
I just. Right.
So it is, you're talking
Yeah,
about
like
10 by
this.
14 is equal to 5 by 7, right?
X. 5 by 7?
10 by 7. 1 divided by 1.4 is 1 divided by 1.4 is equal to 1 into 1 divided by 14 by 10 is equal to 1 into 10 by 14.
Okay. Right.
So your distance at which the net
Okay,
electric
now
field
that's all
is
right. Okay.
0 from 2 microcoulomb is this 5 by 7.
5.7. Okay, I got it now.
Understood?
Right.
How was
Yeah,
it?
I got it.
Did you understand?
Good, good. Yeah, I did.
Okay. You have to practice, otherwise you will forget it.
Right, right. I will.
If you go to SL, whatever book you're using, and go to the unsolved part of it, you
Okay.
should do few questions with your own, in your own self-study time. Go to 1.59
Okay. Of what book?
SLA.
Okay, I'll do that.
Go to page number 1.5, example 69.
Okay.
Do you see? 59, 1.59.
Let me open the. I have a PDF of it.
Okay, you don't have the physical book? Also, you don't have it. Okay.
No, not Sylindrical. I only have MTJ fingertips.
Go to MTG, find questions on linear charge density and do them. I will send you some. I will send you some questions.
Okay, okay.
Right? Please practice them.
Okay, well,
Before you come for the class tomorrow, please do 2 numericals, which I will check.
okay.
We are meeting tomorrow again.
What time
time
is
would you like to
class
meet?
tomorrow?
Tomorrow, preferably, I will confirm back to you. I will just discuss and let you know, because tomorrow generally I don't teach.
We can, if you want. Okay,
Yeah.
okay. We can do earlier if you want. Like in 2 p.m. your time.
Okay.
Today.
Let you know. Sure. That is a good time to
Okay,
have.
yeah.
I will confirm back. I'll
Okay.
let you know.
Okay.
All right.
All
Thank you
right,
very
I
much
will.
for your time today. And please do
Okay.
go and revise. It will help you
Thank
immensely.
you.